Morning, everyone. Welcome back to our C++ course, our parallel computing course with C++. Last time we talked about linear algebra and tried to analyze what influence different, how can we utilize the properties of the hardware in order to improve the performance of our codes. And we got an insight into the fact that the locality of where the data is has an immediate effect on the overall performance. What I want to do today, and by the way, today's lecture is the last one that focuses on single core performance. Okay, we have talked about parallelism here and there a bit, kind of as a glimpse into the future. But today we will finally reach the point where we will stop. Well, after today's lecture, we will stop talking about single core performance and I will start talking about parallelism next time in earnest. So things will really get interesting. But before we do that, in today's lecture, I want to cover two topics that are very important in the context of performance, in the context of scientific applications. One is we will introduce the roofline model, which is a visual tool that allows us to objectively assess the performance of our applications by comparing the performance we have reached against what the hardware can actually do. What are the hardware limitations and how do we perform against that metric? The second thing I want to introduce today is sparse matrices, because in scientific application, we mentioned that linear algebra, working with matrices, is absolutely crucial and central. But very often we find ourselves in a situation where the matrices are immensely large, hundreds or thousands or even millions of lines and columns in the matrix, but 99% of the values in those matrices are zero. So they don't contribute to the overall computation and we can leave them out. So we will talk about what's called sparse matrices, sparse linear algebra, or at least we will start touching on this, just to introduce how we can handle the case when we have essentially matrices that are almost empty and that have no values. And that will give us some interesting insights again into how we can utilize hardware performance. So the roofline model. One of the things we really want to understand, and we always come back to that, is what is the performance of our applications? But we never really defined what do we mean by performance. Is it really just the gigabits or gigaflops we reach? Is it the percentage of peak performance we can reach in our applications? This is not really a measure because that doesn't give us a understanding of how well our algorithms are being implemented. So what we have seen is that the computational part of our algorithms is really, really fast, right? We said that multiplication, addition of floating point numbers essentially takes one cycle, which is on modern cores, half a nanosecond, essentially. On the other hand, we always saw that moving data to and from the main memory into the registers of the cores is very, very expensive and can take up to 200, 300 cycles just to fetch one value from main memory into the cores. So we have to analyze both limits, right? On one hand, we have a limit in terms of what the computer can do in terms of floating point operations, theoretically. And on the other hand, we have to think about how much data can we actually move from and to the main memory in a certain amount of time. So we are interested in bandwidth, which is the amount of data we can move, latencies, how long does it actually take to do that operation, and peak compute performance. So if you kind of start formulating a simple formula and say, okay, for us, performance, we want to measure in gigaflop per second. How many billion floating point operations per second can we actually perform? And we said, okay, on one hand, this is limited by the CPU peak performance. And we can look that up. We can look into the manual and they will tell us, yeah, this CPU can do, I don't know, 50 gigaflop per second or something like that. On the other hand, when we talk about memory, there is another limitation, right? If we are not able to move all the data fast enough in and out of the core, then suddenly the memory bandwidth, the amount of data we can move, turns into the limitation that limits the performance of our algorithm. Okay, and the performance is the minimum of those, right? Either we can reach peak performance or we are limited by the memory bandwidth. If you look at the units of measure of these things, then we said, okay, performance is gigaflop per second. It's easy. The peak performance is gigaflop per second as well. Great. But bandwidth is measured in gigabytes per second. So something is not quite right in our formula here. So what we have to do, we have to find another measure that gives us actually gigaflop per second in order to match the physical units, just from that standpoint. So we have to find some coefficient lambda here that is measured in gigaflop per gigabyte or flop per byte. And when we multiply that with our bandwidth, we actually get our performance we are looking for. And if you remember last lecture, we started to introduce or calculate something we called numerical intensity. It's how many floating point operations can we actually perform per byte read from the memory or byte moved to and from the memory. So we call that numerical intensity. And that gives us a very good picture of performance. On one hand, our performance is limited by the CPU, what the CPU can do, what the clock rate is. On the other hand, performance might be limited by how numerically intensive our algorithm is. How many floating point operations do we get out of one single byte we load into the core? Do we get 10 or do we get 0.10? And that certainly defines whether we reach the bandwidth of our machine or not. If you are able to load to do a lot of floating point operations just with a very small amount of data, then most likely you will not reach the bandwidth limitation, right? Because you're reading only a very small amount of data and you can do all the computation you want on that small amount of data. So bandwidth is probably not the problem. On the other hand, if you have a very a low numerical intensity, that means that you can do only a few floating point operations, but you need a large amount of data to do that, then the probability is very high that you actually run into bandwidth problems because you have to move all that data from main memory to the core. And since you can move only so much data, because there are bandwidth limitation to the core, you will not reach the peak performance anymore because, well, the core can't do as many floating point operations as you want or as theoretically possible because there is not enough data available to do that. Okay, so if you look at that and plot a graph and say, okay, we have x-axis, our numerical intensity, y-axis is the gigaflops per second, gigaflop per second we can achieve. Then we can immediately put two graphs on that plot. One graph is the CPU peak performance, which is constant. It doesn't depend on the numerical intensity. It's a characteristic of the hardware we're using. I don't know, 45 gigaflop per second or something like that. Depends on the machine you're working on. On the other hand, the bandwidth is something that is a kind of a sloped line because it depends on the numeric, the maximum performance you can reach depends on the numeric intensity. So if you have a very low numeric intensity, then you have to move a lot of data for only a few operations. And that means you're hitting the maximum of achievable performance very early on. So what this line gives us, or what this graph gives us, is a maximum of achievable performance for a particular platform given a certain numerical intensity. So everything below these two lines is possible. Everything above those lines is theoretically not possible. Okay? And that's why it's called the roofline graph. This is kind of the ridge point. And if you squint at it, it kind of has a shape of a roofline. That's why it's called roofline model. The slope of that bandwidth graph is our gigabytes per second, is how much data can we move in a certain amount of time. If you look at a single core, what we see is probably something like this. So I just made up some numbers. Let's say our core can do 3.5 gigaflop per second and has a certain bandwidth. Now, if we start looking at vectorization with SSE architectures means that we have 128-bit vector registers. That means we can do 2 double operations per cycle. On a single core, we can do 1 double operation per cycle, 1 floating point operation per cycle. When we vectorize on SSE, we can do 2 floating point operations at the same time, right? Because 2 doubles are being loaded in a vector register, and then the floating point operation is performed on the same cycle on both double values. What does that mean? Well, that means that we now have a much higher peak performance. So we move our roofline up, and that increases the amount of theoretical performance we can achieve. Well, let's play that game even further and say, okay, if we have AVX vectorization means 4 of those doubles in one register, right? The registers are 256 bits. And that means we get even larger peak performance because, well, now we have 4 floating point operations per cycle. So that gives us 4 times more theoretical peak performance on our cores. Now, architectures support something that's called fuse, multiply, add operations. So that's special instructions that perform a multiplication and an addition in one cycle at the same time. If you give it 3 numbers, it will perform that multiplication and that addition in one operation. That, again, doubles the amount of operations we can achieve, right? So that gives us yet another roofline that corresponds to using fuse, multiply, add operations with AVX 256-bit registers. No surprise so far. On the other, so let's look at the bandwidth. So let's say we have a bandwidth of 70 gigabytes per second, and let's say this is the bandwidth we can achieve when we work from level 2 cache. And this kind of corresponds to reality. Just to remind you, the number of cycles roughly spent to load data from different levels of the memory. If something is in the register, it takes 1 cycle to access that, so you can directly work with the data. If you have level 1 cache, it usually takes 3 to 4 cycles to get that data into the register to work with it. Level 2 cache, about 14 cycles, 3, 75 cycles. And if you have to go to main memory, we actually have to wait about 200 cycles in order for that data to come in. And that already tells you where the problem is, right? If it takes 200 cycles to read a single double from main memory, that means that I can't do any floating point operations for 200 cycles. So I'm wasting a lot of compute power, and the bandwidth, the time it takes to load that data from main memory turns into the bottleneck for the overall performance, because we can't even do the floating point operations because we don't have the data available to us. Okay, so if we draw these additional lines, bandwidth, on our roofline model, we see, just as an example, for level 1 cache, we get another sloped bandwidth graph here. And if we add the main memory to it, you see that it's way lower in terms of achievable bandwidth. So to kind of summarize, what we see is that if we have a certain algorithm, and that algorithm has a property, exposes a certain numerical intensity because of what it is doing, then we can use that numerical intensity and see what is our theoretical peak performance if we assume that the data we're working with is located or has to be fetched from different places in the architecture, on different levels of the hierarchy. On the other hand, if we know that, well, we measured our algorithm, we said, okay, we found out that, let's say our algorithm has a performance of 5 gigaflop per second. So we go in with a 5 gigaflop per second and see, okay, what numeric intensity do I have to achieve in order to be able to afford loading things from far away memory, right? The further I have to go right, so the higher my numeric intensity is, the farther away the data can be from the core in order to still achieve the performance we are interested in. The other thing that needs to be said here is that if a code or the performance of a particular algorithm is in the range as limited by the bandwidth, we say that it's memory bound. So the algorithm is memory bound. On the other hand, if you have an algorithm that happens to be limited by the peak performance of the core, so somewhere here, then we say it's computer bound or computationally bound. One example for a real measured roofline graph. And by the way, the assignment I just posted will ask you to create that roofline graph for the architecture you're working with. Has anybody already done or looked at the current assignment? Well, I know Panos has. Nobody else? Well, then just see it as an introduction into what you have to do there. There will be a script that will generate this kind of graph for the machine you're working with. So you get a understanding of what are the theoretical limits for the architecture I'm working with, which is very important. Okay, so let's look at an example. Let's say we have our matrix vector multiplication for dense matrices and dense vectors. What is the numerical intensity of that? If you look only at the loop body of the inner loop, we see that per iteration we do 2 floating point operations, an addition and a multiplication, and we have to move 3 doubles in and out of memory, right? These 2 doubles are moved into memory, and that double is moved in and out of the memory. So we get 24 bytes that are being moved. Overall, if you look at the whole function, we perform about 2 times n squared floating point operations, right? We have a matrix which is n squared in size, so the overall amount of floating point operations is 2 times n squared. Whereas the number of bytes moved is roughly n squared, that's a matrix. 2n is the 2 vectors, y and x, and that gives us 8 times n squared plus 2n bytes that we have to move in and out of memory, which gives us a numerical intensity of about 1/4. So we have 1 floating point operation per 4 bytes moved into the core. If you look at our roofline graph, that means we have about 1/4 floating point operations per byte. And if you assume that all the data is located in main memory, and we have to fetch everything from main memory because nothing is in the caches, we achieve a theoretical limit of about 3 gigaflops per second. 3 gigaflop per second. If we look at the matrix multiplication, and we still assume that we can't reuse any data, we have to read every value from main memory, nothing is in the caches, then we get, again, 2 floating point operations on the inner loop, 3 doubles moved in and out, 24 bytes, and the whole thing has about 2 times n cubed floating point operations and 24 n cubed bytes, which gives us a numerical intensity of 1/12, so much worse. Again, let's look at our memory bound graph, at our roofline graph. About 1/12 bytes, flop per byte. That gives us a theoretical limit what we can achieve on that particular architecture of about 1.4 gigaflop per second. Now, if we compare that with a graph we actually saw last time, right, where we're plotting performance graphs, we see that in this case, for very large matrices, we can assume that the matrices have to be loaded from main memory, so we don't have any caching, we don't have any benefit of having part of the data close to the cores. And if you compare that value to the theoretical limit we have, 1.4 gigaflop, and in practice we actually measured 0.4 gigaflop, we see that we are very close. So at least in the same ballpark. The reason why it's smaller is, well, this is a theoretical limit. We didn't take into account all the integer operations we have to do, right? In order to access an element in the matrix, we have to do an integer multiplication, and we have to calculate the index, and there's a lot. The looping logic has some additional things that are happening that are not being taken into account. So the overall performance we achieve is a bit larger, a bit smaller than what's theoretically possible. So things still make sense. Now, let's have a look at the same thing, at the same algorithm, and assume that we can reuse everything. That all three matrices are loaded in a memory that is very, very close to the core. And that brings us very close to GPU architectures, by the way, because GPUs have a certain memory architecture that allows to preload things into a very, very fast memory that is very close to the GPU cores, which gives us very short access and very high numeric intensity there. Okay, so let's do the calculations. And again, inner loop has two flops, two floating point operations. We still move 24 bytes. But we have to load each element of the matrix only once, because we load it, then it's close to the core, and all subsequent iterations over that algorithm can use things that are very close, because we assume that we can reuse the matrices completely. The amount of operations is still 2 times n cubed, but since we now don't have to load that data on each iteration, we have to load it only once. We have only 24 n squared bytes to load, much less. We load it once, and then we do the whole operation without additional load operations. That means we have a numerical intensity of n over 12. And this is an interesting case, because now our numerical intensity suddenly starts depending on the size of the matrix. So the larger the matrix, the higher the numerical intensity. If you look at the roofline plot, we see n goes up here. That means that for some n, we suddenly are not limited by the bandwidth anymore, because everything has been loaded to memory, right? There's no memory load happening anymore after the first iteration. And that gives us a peak performance that is limited by what the core actually can do. And even if we increase the amount, the size of the matrices even further, we will not reach better performance, because, well, the core can do only as many floating point operations per second, no matter what you do, right? Okay. If you look at that graph we produced last time, we see that we had the best performance in that region. And this is roughly, well, if you look at the dimension of the matrix, you can kind of say, okay, this is a region where the matrix fits into level 2 cache. Level 2 cache is large enough to hold all of the matrix. So once it's loaded once, you can reuse that matrix over and over again for the full duration of the matrix multiplication. And we achieved about 5 gigaflop, which is close to what the closer to the theoretical bound, right? Our graph told us that we can achieve theoretically 45 gigaflop, but this assumed that we have everything in the registers, right? Very, very close to the cores, no time needed to load things. But here we are in level 2 cache, and level 2 cache had about 40 cycles to load things. So there's still some overhead. It's not quite absolutely cheap, and that limits our achievable performance in that case, right? Okay, so you see that, well, if you look at the graph with the same numbers, we have 5 gigaflop, and if you assume level 2 cache, well, the achieved numerical intensity is somewhere 1/10 or so on that concrete example. So you see that we can use the roofline plot in two directions. We can get from the numeric intensity to the achievable performance if we know where the data is, or we can measure the performance and say, okay, it fits into level 2 cache, so this is roughly the real numerical intensity we have achieved with our algorithm. So it's a very useful tool that visually gives you a good understanding of where is your performance of your algorithm. You can always assess how good is my implementation. what limits my implementation? Where do I have to look? What do I have to improve in order to get better performance out of that? Okay, so in summary, roofline model, very useful. Use it for your purposes. It's the model to understand the real performance of your code, because it allows you to assess how good is my implementation compared to what is theoretically possible for this particular hardware I'm running on. Any questions about that? No? I think it's easy to understand. It's a very useful tool to have, and the Docker image you will download for the assignment has a script and some code in here that will run for about 5 minutes, will do some performance measurements, and will in the end produce something like that, so that you get a good understanding of what the machine can do. And we will use that in the future for you to actually understand how good is your implementation of the algorithms, because then you can compare it to the roofline graphs you generated for the machine you're working on. Okay, so far the roofline model. Now let's switch gears and talk about sparse matrices. As always, in this course, I want to start with a very, shallow introduction of the mathematical background of all of that. In many scientific applications, you are solving systems of partial differential equations. Examples are heat transfer. If you put a pizza into the microwave, you have a heating on one end, and you want to understand how is the heat distributing across your pizza, so you know when you have to take it out of your microwave. And by the way, that's why it's turning, right? So that the heat is better distributed over the whole pizza. The way that is done is very often based on so-called Laplace equation. The intuition for Laplace equation is the following. You have some region in space, the pizza, where you have a function phi defined, which could be the temperature, and you don't know what the distribution and the values of phi inside that square is, but what you know is how phi is changing on the boundaries. So you know the first derivative of phi on the boundaries, on delta omega. What you want to achieve is you want to extrapolate from the change of phi on the boundaries. You want to extrapolate the values of phi inside that square with best possible smoothness. So you want to create a function, a distribution of values inside that square that is as smooth as possible, but still conforms to the changes on the boundaries. Okay? What does it mean, maximum smoothness? Well, maximum smoothness means that, or one way to represent maximum smoothness is to say my second derivative of that function should be 0 on average. And that's why we do this. We find the second derivative of phi over that space and over time and set it to 0 and solve that system of equations. And once we have solved it, we will get the values of phi inside that square that give us best possible smoothness given the boundary conditions on that square. This is called Laplace's equation. That's the whole thing. Okay, so always keep that in mind. This is kind of a very easy intuition. I don't want to dig into all the math here and all the background, but from that intuition you see where this is going. So Laplace's equation on the unit square is really the prototypical representation of a partial differential equation. And many problems in physics are being representable that way. Heat equation, wave distribution, electromagnetic behavior, all kind of different physical phenomena can be described using this equation. So as always, when we want to solve some problem from the scientific computing, first we have to discretize the problem. Remember, that was the first step in getting to a solution. So how do we discretize it? let's do some trivial math. So the first derivative of phi is d phi over dx plus d phi over dy, because it's partial, right? You want to differentiate across the two coordinates. The second derivative is very similar. And if we start approximating that and say, okay, how does these formulas are for one dimension only, for simplicity. So if we have a function x which changes over time, t, then the derivative of that function x over t over time can be approximated by taking the value on the at time plus some delta minus the current value divided by the delta, if assuming that the time step is as large as the distribution across space. So the second derivative can be approximated using that formula, and as you see, it's essentially taking the next time step plus the previous time step value and subtracts twice the current value in between those two time steps and divides it by the square of our delta. If we move that into two-dimensional space where we have two coordinates x and y, and we want to find the approximation of that function in space for each of those squares, we actually come to a generalized formula that looks like this, which tells us that the value of, at the point when we reached a stable solution of our dynamic system, the value of each element, which is phi ik, is defined by the average of the four surrounding phi's. The phi I plus 1, j, I minus 1, j, I j minus 1, and I j plus 1. So our x is essentially the average of the four surrounding points of that particular point in our matrix. Once we reach the stable state, right? Once this equation is equal to 0. And that's where we want to get. So for each point x, y in our mesh, we know that point x is the average of the four surrounding points, which is ij, minus 1, plus 1, and the same in the other direction. Okay? If you want to turn that into an iterative process to get to the solution, we introduce time and we say, okay, these are our time steps. K is time step, and we compute the value on the next time step of each of the points by computing the average over the surrounding points. So we get the value on the next time step based on the values on the previous time step by averaging the surrounding points. So we have the surrounding points and we use it to compute the new value of x on the next time step. And that's how things are being, that's how you solve these Laplace equations. By doing that computation, that averaging on each time step for every element in your mesh. And you repeat that on each time step. So you go over that mesh once per each time step, computing a new average value of the surrounding points. And when you do that long enough, then things stabilize and the values will not change anymore. Here's a simple code that is doing exactly that. So we have two loops, one over I, one over j. And what the body does, it just takes the surrounding 4 points of I and j, divides it by 4, and sets the result to the corresponding value in the result array. So we need two arrays, x and y, x representing the previous time step, y representing the time step to be computed. And once we're done with that, and we haven't converged, we swap these two things and start over. This is a typical example of what's called a stencil code. It's called a stencil because you kind of cut out a certain amount of surrounding points around the point of interest and do some computation on it. In this case, we have a simple cross as a stencil, but in other stencils, in seismology, for instance, you use very large stencils where you go 5 elements in each direction. 5 elements to the left, to the right, up and down. And you can solve the equations that way. Any questions so far? So stencil codes are essentially this. And this is good homework or a good project. If you want to solve the heat equation using stencil codes, well, here's the code. All you have to do, you initialize it with some initial temperatures, iterate over it over and over and over again, and after 100 or 1,000 iterations, you have equalized things and you know what the heat distribution is. Not very difficult. Okay, so while this code is very easy to understand, what I actually want to do, I want to represent the whole thing as in terms of linear algebra, because that is very useful in many contexts, mostly because we don't usually there are already solutions out there that provide you with very highly efficient linear algebra kernels. So you don't have to write a matrix multiplication yourself. You can use something that's out there. So let's reformulate our problem such that we can use existing code that is highly optimized, and that is linear algebra, matrix multiplication, matrix vector multiplication. So if you squint at what we had and assume that we linearize the points in our mesh, just not by addressing the points in the mesh using two indices, but using the single index, then we see that the formula I had before can be rewritten as 4xi, or xi is the average of I plus 1, the points next to it, and I plus n, which is the corresponding point on the next line of the matrix, and I minus n is the point on the previous line of that matrix. So we get a system of linear equations for I from 0 to n squared. For x, we have n squared unknowns, xi to n squared. And we get a system of linear equations we have to solve. So we have a fully linearized solution here that allows us to transform our initial setup, that Laplace formula, into a system of linear equations. So system of linear equations, that means we get a matrix where here are our values of the x's we want to compute. And here are the coefficients on those x's, which is on the diagonal we have a 4. On the two next diagonals next to it we have a -1. And further away we have another diagonal with -1s, which represents the rows and not the neighbors in terms of columns. This thing is called the Laplacian matrix. So it's a diagonal matrix that to 99% consists out of zeros. Just assume we have our unit square. We want to discretize it with a discretization level of 100 elements in x and 100 elements in y direction, or I and j direction. That means that matrix will have 100 rows and 100 columns. But only 4 values or 5 values on each row and 5 values on each column are not 0. That means 95% of the matrix is empty. It has zeros in there. And this is exactly the problem I want to tackle in this lecture. So at a bit more lengthy introduction into the problem, but here you go. So this is a matrix, and if you can solve this system of linear equations, we will get the solutions for x, for our axis, which gives us the distribution, the values of phi we are looking for. So just to recap, we went from the physical description, we discretized it into that formula, and we got to a linear systems of equations, where each of the equations essentially represents 1x is the value of each point in the grid, and it has to be equal to the average of the surrounding points that's the solution we are looking for. So one question you might have, if we start off with all zeros in our mesh, why is the solution not 0? Well, the solution is not 0 because we have the boundary, right? The boundary is non-zero. That's a trick, because the heat is kind of moving from the outside in. And that means we have a non-zero right-hand side of that system of linear equations, which is determined by the boundaries. Okay, So far, so good. Any questions about that? If you're more interested in understanding how that discretization works, there's plenty of information available. You can find plenty of information about the Laplace equation and how to discretize it. So this is really well known. And if you decide to do your project by applying that, you will find plenty of information out there, much more than I can ever teach you. The other option is just take a course on numeric methods, and they will teach you more than you ever wanted to know about these things. Okay? Anybody has taken numeric methods? Yeah, so you know what I'm talking about, right? So this is not rocket science in the end. Okay, so now let's tackle the problem that 95% or even more of that matrix is empty, is zeros. If you look at our matrix multiplication algorithm, that means that if A is our Laplacian matrix, that 95% of all operations will produce 0, because either A or B are 0. How can we tackle that? What can we do about that? Because why should we do multiplication with 0 when we know that we get 0 out of it? So we would waste a lot of computational resources in order just to multiply zeros with some values. So the solution is, hey, let's be smart. Why don't we just add an if statement there and say, do the multiplication only if both are non-zero? Both terms on the right-hand side are non-zero. Well, why don't we do that? Why isn't that the solution? You save on floating point operations. Yeah, sure. Do you save on memory movement? Not at all, right? Because you have to read that stuff anyway, and you have to look at the values before you do the computation. So this is not good. We still touch every element, and that's what's expensive. It's not the floating point operations that we want to save. We want to save on data movement, because that is much more expensive than the operations themselves. So we need to avoid the zeros without looking at the values to see whether they are 0. And that's where the crux lies. So in order to avoid zeros, what we will do, we will not store them, which also saves memory. Because, well, if that matrix is, I don't know, 1,000 by 1,000, and 95 or 99% of that is zeros anyway, why should we store 99% of that million elements if we know that they are 0? All what we need essentially is 3 diagonals or 5 diagonals, which is 5,000 elements instead of 1,000,000. So we would save a lot of memory if we were able to store things in a way that the zeros are not even stored in memory. So what we will do, as always, when you are looking for a solution, when you try to optimize, it's always the algorithmic change and the data structure change that gives you the best performance benefit. So let's change the data structures to store all of that, and let's change the algorithms to play with those data structures. And those are called sparse matrix techniques. Now, we have to solve a linear system of equations, and there is a lot of prior art about that. But the problem is that if we use direct methods that work very well with dense matrices, if you work with sparse matrices, if you remember how linear systems of equations are being solved, you have to somehow do the Gaussian elimination, which changes the coefficients on all elements of the matrix. And that means that we probably will get non-zero values on many of the elements that are 0 currently, which is a lot of effort. We don't benefit anymore from not storing the zeros, because once we do the Gaussian elimination, we have a lot of elements that are non-zero after all, so that doesn't work well. There are iterative methods available that create successively better approximations of that of the solution for the linear system of equations. There are so-called relaxation methods, Jacobi methods, but they're very, very, very slow, very difficult to parallelize. There are Krylov subspace methods. Again, second-order algorithms. Krylov algorithms are second-order algorithms, so they work very well. I talked about that. And one of them is the conjugate gradient method. We might talk about conjugate gradient at some point if time permits. But you still have to have very good preconditioning for that. But let's look at these iterative methods and what is needed to implement these iterative methods to solve our system of equations. What I have on this slide is purely an aside which gives you the algorithm for a conjugate gradient solver for a linear systems of equations. And I don't want you to memorize that or anything. What I want to highlight is that one of the central pieces of things that are happening in that conjugate gradient algorithm is a matrix vector multiplication. And that's why for the remainder of the lecture I want to focus on how to implement matrix vector multiplication for sparse matrices. The methods applied there can be applied to all the other operations in the same way. But this will give us a very simple example that makes it easy to understand what's happening with these sparse matrix algorithms. Okay, so a matrix is a map from two indices to a value. If we want to store just the elements that are non-zero, we need to store not only the value, but we need to store the indices of that value as well, right? So if that is our dense storage, and remember we talked about that, dense storage means you have the values, let's say in a row major order, you store it in a one-dimensional array. The second row comes after the first one, third row, fourth row, and so on and so on. So this is our dense storage representation we have been talking about. So all matrix elements are kept at the location that corresponds to their position in the matrix, right? And that's what we want to get rid of, because as you can see, there are a bunch of zeros. Why should we store those zeros if they don't contribute to the final multiplication result we're interested in? So if you look at what we do with that multiplication algorithm when we multiply a matrix with a vector, we see that we go through all possible valid indices and all values of A for the dense matrix, no matter whether it's zeros or non-zeros. So with the dense storage, we loop through all the possible indices and look up the corresponding value. Obviously, that's what we have seen last lecture already. If you want to create a sparse representation of that matrix, and we want to get rid of all the zeros, in the end, what we will store in memory is really just the values of the non-zero elements. So the 3 is there, the 8 comes in, the 1, the 4, the 6, and so on and so on. So we store only the non-zeros in our one-dimensional array underneath. And our goal is to loop over all the indices for the non-zero entries, but since the non-zero entries is not a property of the matrix, the algorithm has to know that. The matrix can't tell us where, that representation can't tell us where things are, right? So we need to store the indices as well, so that the algorithm can figure out at what ij is the 8 actually located. In this case, it's 0, 3 probably. So we have to store that somehow. So let's store these values together with our actual values. Here are the indices. The 3 is at 0, 0. The 8 is at 0, 3. The 1 is at 1, 1. The 4 is at 1, 2. The 6 is 1, 4, and so on and so on. One interesting question is, now, does it matter in what sequence we store these things? Does it matter? It doesn't matter anymore, right? Even if we flip these two things, we still have the same matrix, because we store the position of the value together with the value. So, and that's an important insight, and we will see how we can utilize that, that the sequence of how that is stored in memory doesn't matter anymore. That's why let's have a look at how how can we represent that information in memory? And there are two ways we can do that. And these two ways are called array of structs and structs of arrays. So let's look at the array of structs representation. We have every element represented by 3 values. Each element has 2 indices and a value stored. And each element is essentially a single array with 3 element structs. So it's an array which has a struct, and the struct has 3 elements: the column, the row, and the value. Right? So our element we want to store has these 3 values: the row, the column, and the actual value. And we store a vector of these elements in our coordinate format matrix. COO format is the short form for coordinate storage. So you can Google that. COO is a commonly used term for that. So that's one way of storing things. We have one single array where each array element has these 3 values we are interested in. That's why it's called an array of structs, because we create one array where each element is actually its own data type, the element. Now, the other option we have is what's called struct of arrays, where we have 3 independent arrays. Again, we store all 3 values for each of the values in our matrix. So each element has 2 indices and a value stored. Still the same thing. The difference is that one array has the row indices, the second array has the column indices, and the third array has the element values. And the index, the values that sit at the same index in those arrays belong together. And that means that our COO matrix representation now looks like this. We have 3 vectors, one for the row indices, one for the column indices, and one for the values themselves. The question is, which one of the 2 is faster? What would you say? Array of structs or structs of arrays? Yes?
You asked which one was better?
Yes, which one is faster?
Array of structs.
On what architecture? Well, there is no direct answer, because array of structs is faster on GPUs and struct of arrays is faster on CPUs. And you can try that out. Feel free to write some code, do some measurements, figure that out for yourself. Okay? Which, by the way, is a big problem, because when you combine CPUs with GPUs, people very often convert the format when they go from the CPU and send data over to the GPU, have to do some computing there, and then they have to go back. They have to convert the data again. So in codes that use CPUs and GPUs at the same time, you very often will see code that actually transforms things from structs of arrays to arrays of structs. But as long as we are on CPUs, struct of arrays is a bit faster than arrays of structs. And that is mostly caused by cache alignment and by cache properties and things like that. Okay? Any questions about that? Okay, well, let's go on. If you look at the performance comparison between sparse and dense matrix multiplication for that MATVEC, it's a matrix product here, for the same matrix size where one has a bunch of zeros and the other one has a sparse representation in coordinate format, we see that the sparse representation performs much better. Is the execution time. So the sparse representation performs much better than the dense representation, obviously. And the reason is we move much less data to the cores and we do less floating point operations. So that's completely expected. Okay, so all good, but no. There are quite some problems because we don't know how to implement all of that yet. Just as a reminder, this is the matrix class we have seen in the assignment and we have shown last time. And the nice thing here is that the matrix class has operators that take the 2 indices and give us a reference to the element these 2 indices represent. So we give it the indices, it computes the element in constant time. So in order to find the element in the storage, independently of the values of I and j, it takes the same amount of time to compute that, right? Because it's just a multiplication with an addition and it doesn't depend on the values. So that's very important, and that's a benefit of the dense matrix representation, that we can get to the element we're interested in constant time, in O1 complexity. Now, if you look at the COO matrix, the coordinate format matrix, we have the three arrays, and we also store the number of columns and the number of rows separately. But how do we get at the element we are interested in if we provide I and j in constant time? Well, we can't, because there's no way. We would have to scan through the whole array until we find the pair of I and j, and then we know which value we're interested in. So the access time for such an operator, that we give indices and that gives us a reference to the value we're interested in, would be linear. So a very large matrix would take a very long time to find the element, because we have to go through that array and see whether we actually have that element or not, right? And in the worst case, we have to go through the whole array and figure out in the end that the indices are not part of the sparse matrix. So we would even have to go through the whole thing over and over and over again in 99% of the cases, just to find out that it's zero. So that would defeat the purpose. So we can't. That's the first problem. The next problem is the following. If you look at the dense matrix multiplication with a vector, we have that very nice property that we can access the element of the matrix directly, as said. And we can do that with that operator. How do we do that with a COO matrix, with a coordinate matrix? There is no way of doing that. So how do we want to represent that computation here in that inner loop in order to get what we want? Let's try to look into that, and let's try to solve that puzzle. Let's go back again to the dense case. And we see here that our inner loop has three things. It accesses y using one of the indices, which is a row index. It accesses a matrix that represents the value at ik, and it accesses the vector it multiplies with using the column index, right? But we have these three things available in our format, in our coordinate format. We know the row index, we have the column index, and we have the value. So these three things are available to us. They are not just available in that very nice way as we can do it with a dense matrix. So let's have a look at what we can do. Here's our COO matrix. What I have done, I have made that matrix vector multiplication to have turned that into a member function. So it's not an external function to the class anymore as before, but it's a member function of the COO matrix. And it doesn't receive the matrix itself as an argument, because it's a member function on the matrix. All that it gets passed in is the x, the right vector, and the reference to where the result should be stored. Now, if you look at the loop, we see the following. We go over all elements in our storage, because those are the elements that are non-zero. That's where we want to do the multiplication. And assign it to and use the row index from the current element k as the index into y. We use the column index at position k as the index into x, and we use the value itself as the value of the matrix we're interested in. And that gives us exactly what we want. We have a loop that goes over all elements that are non-zero, and for each of the elements that are non-zero, it does the appropriate computation by using the row indices, the column indices. We store them together with a value, and we can do our multiplication that way. Okay? If we assume that we have a problem size that is 10 times larger, then the sparse matrix, the code I showed you, is roughly n cubed faster, 1,000 times faster than the code we use for the dense matrices. It certainly depends on the problem size, but this is the benefit you get. And if you look at that graph, it's logarithmic after all, right? So you see that the difference between the two graphs is very large for larger n. Okay, so what's the numerical intensity of that algorithm I just had here? Well, we have to move 3 doubles and 2 ints. We have now more data to move because we have to access the index arrays, the column indices and the row indices. That gives us 32 bytes. 2 floating point operations. That means that we have a numerical intensity of 1/6. So it's a bit worse, but we have to do a lot less operations because 99% of that matrix is not there, right? We save 99% of the work. If you look at our roofline graph, well, we achieve about, I don't know, what was it, 1.2 gigaflops with that code. Okay. The other question we have to answer is, how do we get the values into that class? We can't directly access it through x and y anymore because this formula, this access scheme will work only if we have values stored in the matrix. We can't initialize it that way. So we have to come up with an additional initialization code which will add another function to the COO matrix, which I just called pushback. And that pushback function receives the indices and the value and just adds it to the corresponding arrays as it goes. So initialization of sparse data structures is a bit more complicated than initializing the dense matrix, dense data structures. But here you go. If we call pushback once for each element in our matrix on our COO matrix, we fill it with the values we need, and we can do the computation afterwards. And by the way, in this case, since we said it doesn't matter in what sequence things are being stored, it doesn't even matter in what sequence I call pushback for I and j, because things are being stored in a one-dimensional way anyway, and the sequence of these things doesn't matter, as we have seen. Okay. You can also append elements later, by the way. If you find new elements you want to add, you can just call pushback later on. So that's one of the benefits of that COO matrix, which you can utilize in your code. Now, can we do better? Can we save even more memory in order to reduce the amount of data that is being stored in memory and that has to be moved from memory to the cores? Well, we can, because people have come up with so-called compressed sparse storage formats, and there are many of them. The most important ones are compressed sparse row format and compressed sparse column format, CSR and CSC. Let's look at how that looks like. Okay, so I have that matrix again. I have created outlined the values in our 3 arrays. Here, each array stores the same number of elements because each array has to store the number of non-zeros. But if we sort the arrays either based on the row indices or the column indices, you will see that the values actually repeat, right? You have 2 zeros, 3 ones, 1, 2, 3 threes, and so on and so on. And the number of repeats here corresponds to the number of elements in each of the rows. So can we compress that? Can we get rid of the duplication of these values? Because what's the point in storing them? It's the same value. Hey, why should we do that? So let's look into that, how we can do that. So just to repeat, if we have a set of unordered elements and we order them, we have to make sure that we don't only sort one of those arrays. We have to sort all 3 arrays at the same time, obviously. Otherwise, we will mess up our data representation. So the values stay together while the sorting happens. So, for instance, this element is now here, and you see that the indices are still the same as an original element. Okay, so let's change the representation and say, okay, I have the row indices are now 1, 2, 3, 4, 5. And I additionally store how many elements I have in each of those rows. First has 2, 3, 1, 3, and so on. So that means that row 0 has 2 elements where they sit at column indices 0 and 3 and have the values 3 and 8. Row 1, or the second row, has 3 elements which sit at columns 1, 2, and 4 and have the values 1, 4, and 6. Right? 1, 4, and 6, and so on. But now what we see is that we don't need the row indices anymore. Why should we store the row indices if the values are the same as the indices themselves? Right? The first element has 0, and so on and so on. So why should we store that? There's no point in storing it. And on the other hand, if we now try to rewrite our algorithm we had in order to work with these arrays, what we need is a running index that keeps track of where to start the next row, right? The first row starts at 0, the second row starts at 0 plus 2, the third row starts at 0 plus 2 plus 3, and so on and so on. So this row pointer, it's kind of running index. And our loops now work through that compressed data structure by using that run length, which is stored in the second array. Otherwise, the code is absolutely the same as before. So there's no change. The only difference is that now I have to keep track at where does my row start, because all I have is a run length for each of the rows. But even better, we don't even have to compute the run lengths if we can just store the run lengths. Why not store the starting point of the next row in our run lengths directly without having to keep track of that? So the first row starts at 0, and the second row starts at 2. That means these 2 are elements in row 0. The next row starts at 2, goes to 5, so we have 3 elements, and so on and so on. The only thing we have to note is that now the run indices have 1 element more, because what you need to do, you need to be able to represent the last element, which points to the first element after the end of our compressed representation. That's it. So that is your sparse row storage format that people use to represent sparse matrices. And it's, by the way, used not only in linear algebra, it's used in graph computation. Well, graphs can be represented by matrices, so it's logical. You will find that format very widely used in cases where you have matrices that have a lot of zeros and you don't want to store them. By the way, I might just ask you at some point to write code to generate the sparse column representation. So if it happens to happen, just go back to the lecture and do the whole thing, just not with rows, but with columns, and you will get an equivalent result. Okay, so if we get rid of that run length and we store the starting indices for each of the rows in our row indices array, we now have this formula, we have this code where we directly can use I as the row because the outer loop goes over the rows. We can directly refer to the storage using J because that's where we iterate over, and we have to extract the column index from the column indices array and use that as the index for accessing our X values. So same thing as before, it's just using a different underlying representation of the data. One question that is still open is, how do you build a CSR matrix? Because just by pushing back values into the CSR matrix, we don't get that compressed representation. So what people do, they first fill them with triplets of values, very much like the COO format. And once they are done with pushing back values, you have to call a function, in this case close for pushback, which will do the appropriate reorganization of the underlying data structures and will compute the run lengths, indices, and so on based on that format. So in order to build a CSR matrix, you first call open for pushback, then you call pushback as often as you need it with the triplets of values, and then you call close for pushback, after which you have the compressed format in your matrix and you can work with this. Okay. Last slide, performance. Compares the dense performance of dense matrices with the COO and the coordinate format and the compressed sparse row format. Can anybody tell me why the coordinate format is worse for very large matrices and otherwise equivalent to the compressed format? Anybody? Yes? Well, caching is usually right, yeah. I mean, if you say memory, it's always right? So it's not even usually. But the reason is, if you think about it, the compressed format has to move less data, and the amount of data stored in memory is smaller. So the chances for that thing to be still in cache is much higher, especially for very large matrices, okay? So what we see is still the factor of 1 million, and here we see effects of the hierarchical memory, because the more memory you need, the farther away is the data. And the less data you need, the higher the likelihood that things are in caches somewhere closer to the core. And you will see that only for very large matrices, right? For 64 million by 64 million rows and columns. Before that, these two representations are almost identical. But there are problems. I mean, machine learning, right? This is a small matrix in machine learning. This is a tiny matrix in machine learning. In machine learning, you have matrices of billions, of hundreds of billions of rows and columns. And there you need to have a way to represent that efficiently, because otherwise you can't even store that in your computer anymore, because you don't have enough memory. You can't do that anymore. Okay? Good. Any questions about that so far? None? Well, thank you so much for your attention. I'm done for today. And on Thursday, we will start talking about parallelism, finally. Thank you.